This lecture continues the new approach to artificial general intelligence, or AGI, based on two primary principles. The first is based on analysing the information contained in a single English sentence and was covered in part 1 of these lectures. The second, to be covered in this part 2, is based on analysing the information contained in a sequence or group of related English sentences.
Part 1. Guaranteed you've never seen sentence semantics approached in such a radical way before. Part 2. Dialogues and mental models have even more surprises. So keep that mental seatbelt securely fastened. It's going to be an equally bumpy flight.
Let's look at the mental model first. There are various definitions of the mental model. Here we define the mental model as a simplified abstraction of the real world which we hold in our minds to assist us in our lives. Exactly what this involves will become more apparent as we proceed.
Our own mental model is established and updated using data from all our senses. But here we consider just a small part of a mental model, established, updated and queried using an English language dialogue or discourse only.
In early school, we encountered reading comprehension exercises involving reading and comprehending a simple description of something, followed by responding to queries, testing that comprehension. For example, a lady has 2 Burmese cats and 3 Siamese cats. Each Burmese cat has 3 biscuits and 2 toys. Each Siamese cat has 2 biscuits and 3 toys. Count each lady, each cat, each biscuit and each toy.
We build a mental model of the situation from the English sentences and then consulted the model to form sentences responding to the queries. Here we study mechanisms allowing computer software to do a similar thing. In fact, the software application AI Dialog, described later, can understand and respond correctly to the example given. Our study of dialogues and mental models will show us how it is able to do this.
From part 1, you may have started to guess that we can use a semantic network as a foundation for our restricted mental model. This is not necessarily the way our brains and minds hold our own mental model, but it does give similar results in comprehension exercises, as we shall soon see.
Semantic networks have a long history in use in linguistic semantics. To the left is a typical network representing the station example of part 1. You will notice that the links between the nodes represent fairly complicated concepts, e.g. is above, is beside and is below.
But in part 1, we adopted a very rational network representation by allowing only is or has on the edges linking nodes. This became possible because we showed that most English sentences could be reduced entirely to sets of simple is and has expressions. That is, X is Y and X has Y, where X and Y were mostly single sentence words. To the left we see the resulting rationalized network.
Let's now have a look at the form of the sentences within a dialogue, from which a mental model may be built. Sentences generally have 2 components, One specifies new data to add to the mental model, and one whereabouts on the mental model. For example, with the sentence, "The Siamese cat is very fierce," the Siamese cat phrase picks out our Siamese cat data location on the model. The "is very fierce" gives new data to add to our model at this location.
To put it another way, this is very much like updating an IT database. The following is an example of an update to such a database using the IT database query language SQL. So we have update pets, set character equals is very fierce, where breed equals Siamese, and type equals cat. You don't really need to fully understand this to see how it resembles the structure of the previous sentence.
In practice, of course, our mental model database is far more versatile. Our mental decoding of the content of English sentences allows much more flexible data input. But a problem which arises with complex sentence clause structures is that the location on our model and the data to be added at that location tend to get all mixed up. Some complex sentences may in fact mention multiple locations with multiple data updates associated with them.
For example, the sentence, "Jack and Jill each climbs up the steep hill," where Jack and Jill and steep hill already exist on our model, involves separate updates to all three locations. The Jack and Jill locations are updated with climbing, that is, up, and the steep hill location with the two instances of climbing. Sentences with complex clauses can involve even more convoluted updates to our model. Shortly, we'll examine in detail how such updates may be carried out.
Sometimes there is no specific model location given in a sentence, as in, "There are 3 Burmese cats," which means we just add to our model this fact, and in practice create 3 new data locations for future new individual Burmese cat data.
In other cases, a sentence introduces new data and implicitly provides a location for further data, as in the sentence, "A dog has a bone." Here, a dog adds an instance of dog to our model and provides a location for the data "has a bone."
A final component of a sentence is its truth or falsehood. In our terms, we ask, does it represent a proposed valid or invalid update of our mental model? If it is a proposed invalid update, then can we detect that this is so and avoid adding erroneous data to our mental model?
This is a significant topic, dealt with only briefly in this particular lecture. Just a couple of points. We can only determine validity in the context of our model, not in the context of the real world. If a sentence refers to a second cat, with only one cat present on our model, we can detect that this statement is invalid. But if a sentence declares there is a king of France, we generally have to assume this is valid, because our knowledge is limited to just what any dialogue contains.
Now, let's examine in detail the steps in building, updating and querying our mental model. Again, this is not necessarily the way our mind and brain does the same job, but as we shall see, it does give us a system we can study.
Suppose the first sentence we ever encounter in building our model is, "A lady has 3 cats." The first step is to reduce this to is and has expressions alone, as we saw in the Part 1 lecture.
Below, therefore, from Part 1 is the is-has analysis of "A lady has 3 cats." Lady has cat, cat is first, lady has cat, cat is second, lady has cat, cat is third.
From this analysis, that is, lady has cat, cat is first, lady has cat, cat is second, lady has cat, cat is third, we can build the left-hand semantic network. This constitutes the initial content of our mental model.
Suppose we then encounter the sentence, "The second cat is very wayward." This is an update or augmentation of our mental model data. How do we go about modifying the model to add this new information?
Again, the first step is to reduce the sentence to is and has expressions alone. The sentence, "The second cat is very wayward," has the analysis from Part 1 of cat is second, cat is wayward, wayward is very.
As before, we build another network. So the analysis of "the second cat is very wayward," giving cat is second, cat is wayward, wayward is very, results in the left-hand network. But note we have distinguished the second cat and the corresponding part of the network.
This is because the phrase, "the second cat," is headed by the definite article "the," implying that what follows is something already present on our model. This is giving us the location on our model for the new data. This will eventually cause us to search the model network until we find that part of it matching the node edge pattern shown to the lower left.
But this is not the end of the story. The network for "the second cat" has a distinguished node cat, shown lower left, surrounded by dashes. This is the subject anchor. The subject anchor corresponds to the sentence subject root. The cat is the thing which is very wayward. The upper left is very wayward. Network is new data to be added to our model. But note, at the cat node rather than the second node.
But again, this is not the end of the story. The network of is very wayward has a distinguished node wayward, shown to the upper left, surrounded by dashes. This is the object anchor. The object anchor corresponds to the sentence object root. Note this is the attachment point, wayward, for the phrase very wayward, rather than the node very.
The final component of the process is the attachment edge, is corresponding to the sentence main verb. We generally separate this out from the object phrase. the main verb is always is or has, as we have seen from Part 1 analysis.
We can therefore update the network as shown to the left. Note that the connection points are at the nodes cat and wayward and not at the nodes second or very. The connection edge is the main verb is.
Let's review the sentence processing we've just done. It generally involves building a semantic network for the sentence subject and another for the sentence object or complement. We refer to these small networks as subnets. For brevity, we then refer to the main semantic network corresponding to our mental model as the net.
If we encounter the sentence, "The Siamese cat is very fierce," then we form the subnets shown to the left. The lowest subnet is the subject subnet, and the upper one, the object subnet. We also have separated out the main verb is, shown in the middle.
Associated with each subnet, there is generally an anchor node, shown dashed in the figure. If the subject anchor was absent, we would not know whether to attach the new data to Siamese or cat when we found these on the net. If the object anchor was absent, we would not know that the new data attachment point was fierce rather than very. The verb then tells us the attachment edge type is or has.
Moving on now, let's see how we can query our mental model. Suppose we encounter the sentence, "The lady has how many cats?" How can we manage to create a reply to this query?
Again, the first step is to reduce the sentence to is and has expressions alone. The sentence, "The lady has how many cats?" has the analysis, "Lady has cat." But here there is also some metadata not represented in the analysis, indicating that this is a query. The corresponding subnet is shown below left.
We then search our mental model net to find any pattern that matches the query sentence subnet pattern. As we can see to the left, we get 3 matches, labelled 1, 2 and 3. So we can reply to the query, "The lady has how many cats?" with "The lady has 3 cats."
Let's just pause for a moment to compare sentence semantics and sentence syntax. Various syntactic aspects of sentences need not be represented directly on our mental model. These include plurals, indefinite and definite articles, and anaphoric references. Let's examine why.
Firstly, plurals need not appear on our model. You will have observed that all net nodes used so far are singular. This is because plurals in sentences largely represent purely syntactic information, which is generally semantically redundant.
If we say 3 cats, we really know cats is plural because of the 3. We could just say 3 cat. Occasionally, the plural is significant as in Jack has apple, compared with Jack has apples. We can solve this by adding quantity and number nodes on our model, as shown to the left.
As you will have seen previously, we often create separate instances of several items. For example, in "A lady has 2 cats," as in the upper left of the figure, but we do not have to, as in the lower left of the figure. It depends on subsequent usage on our mental model.
In a similar fashion, all node linking edges so far have been is rather than am or are, and has rather than have. Other declinations associated with tense, for example, was or had, disappear because, as we have seen in part 1, tense is represented by a context.
Indefinite articles, such as a or an or 3, are associated with adding new data to our mental model. For example, if we say "A lady has 3 cats," we add the lady instance and the 3 cat instances to our model.
Definite articles, such as the or each, are often associated with locating existing data on our mental model and updating or augmenting it. For example, if we say the second cat is wayward, we need to locate the second cat on our model and augment it with the data that it is wayward.
But we should note that sometimes we use a definite article, like the, informally to add new data rather than to reference existing data. In practice, we can check which is the case by searching the net for the data referred to. If the data is absent, then the data is new. Otherwise, if the data is existing, then we can just simply refer to it. If more than one existing data instance is found, we know the sentence is ambiguous or invalid.
Anaphoric references need never appear on our model because he has the pail, for example, is replaced by Jack has the pail. This means none of the pronouns he, she, they, or it need ever appear. This also applies to possessive and accusative versions of these, that is, his, hers, their, its, him, her, them, and it.
Although, as we've just seen, plurals, indefinite articles, definite articles, and anaphoric references are absent on our model, this doesn't prevent us from synthesizing grammatically correct sentences from the model when we need to. We still have enough information on the model to form cats from cat, to form a stroke an or the stroke each as needed, and to abbreviate Jack to he or him when appropriate, and so on.
Let's resume now and have a look at a more complex query on our model, a social network. Suppose we encounter the sentences Jack, Cole and Humpty each like Jill, and then Jill likes Jack and Humpty.
After the sentence Jack, Cole and Humpty each like Jill, our model net from part 1 is as shown in the figure to the left.
After the subsequent sentence, Jill likes Jack and Humpty, our model is augmented with data as shown to the left. The new data is added into the right place using the search and anchor techniques described earlier.
Suppose we then encounter the query sentence, list each person that likes Jill that Jill likes. How can we tackle this type of sentence and derive an answer to it?
We begin, as always, by reducing the sentence to is, has expressions. Jill is liking, person has liking, liking of person. Person is liking, Jill has liking, liking of Jill, and building a corresponding sentence subnet shown to the left.
The node person is special. When we start to search the net, the node person will match anything. It's like a wild card. Not only that, but the actual nodes that person matches during the search are of interest to us, and we need to know about them and to record them.
So, the subnet above has the matches shown circled to the left, and from these, person matches Jack and Humpty, but not Cole.
So we can reply to the query, list each person that likes Jill that Jill likes, with Jack and Humpty, as the wildcard node person matches these.
Let's have a look at an assertion example. Suppose we have an assertion such as Cole likes Jill, and we need to determine its truth or otherwise. We again begin by reducing the assertion to is, has expressions. Cole is liking, Jill has liking, liking of Jill.
Then we form the subnet above from Cole is liking, Jill has liking, or liking of Jill, and we then search the net with this. And if we find the match shown to the left, we answer true, otherwise we answer false.
Let's pause again to look at another aspect of semantic networks. So far, network nodes have represented single words, abbreviations or phrases. But there is both a requirement and a potential for nodes to represent more complex items. These include strings, text files, folders, images, context, and other data types.
Of particular significance is the potential for a node to contain a context. A context is effectively a self-contained semantic network. But because nodes within that network can in turn contain contexts, we can effectively nest contexts.
We can then use nested contexts contained within nodes to represent the earlier past pluperfect example from part 1. When Jill arrived, Jack had climbed the hill. Jill's arrival is in the past. Jack's climbing is even further in the past. So Jack's past context is held in a node that is past, which is in Jill's past context, which in turn is held in another node that is past.
There are other examples of nested contexts held within nodes which are parts of further contexts, which in turn held within further nodes, and so on. An example we encountered earlier in part 1 was Jack says Jill will carry the pail. Here we have a future context within a future node within a quoted speech context within a quoted node.
Moving on again, in part 1 we started to examine definitions and instances. Let's look at a definition example first. The definition of a doctor is caring, a doctor is skilled, a doctor has a medical degree. We can use context again and hold the definition in a definition context. This is shown to the left.
Now, looking at an instance example, suppose we encounter the sentence, Jack is a doctor. The semantic net of this sentence is shown in the figure to the left.
But since the definition of a doctor exists, when we encounter the sentence, Jack is a doctor, we can automatically augment our mental model as shown in the net to the left by copying data from the definition. The mechanism is not too dissimilar to using classes and instances in object-oriented software.
Definitions may be nested. So as part of the doctor definition, we may have the sentence, a doctor is a professional, as shown in the net to the left.
And then we can have a definition of a professional. A professional is salaried, a professional is respected, and so on. So when we encounter Jack is a doctor, a double augmentation takes place. Firstly, of the doctor attributes, and then of a professional attributes.
This slide shows the effect of the double augmentation. And again, this process is not too dissimilar to using nested classes in object-oriented software.
Let's now devote our attention to yet another topic, that of sequences or ordering. Ordering can include arithmetical, spatial, or temporal sequences.
Let's look at an example of arithmetical ordering exemplified as follows. 1 is before 2, 2 is after 1, 2 is before 3, 3 is after 2, and so on, with the semantic network shown in the figure to the left. And we can then pose queries such as, what is before 3?
Let's now look at an example of event ordering exemplified as follows. Jack gets the pail, A. Next, Jack climbs the hill, B. Next, Jack fills the pail, C. As shown left, each event is held in an event context, loaded into event A, event B, and event C nodes, which are then ordered using after nodes.
We can also represent events in parallel, as shown below and left. So we get Jack gets the pail, A. Next, Jack climbs the hill, B. Jill watches Jack, B dashed. Next, Jack fills the pail C. Here, events B and B dashed are taking place at the same time. Jill watches Jack at the same time as Jack climbs the hill and then fills the pail.
Let's now have a look at another new topic. It is possible to view and manipulate part of our mental model whilst ignoring the rest. This is called localization. Let's just look at a few sentences on the following slide, illustrating our own mental processes in this respect.
So following through with these sentences, we begin with a control centre has 2 control rooms. Then the first room is main, then the second room is standby, then viewing the first room. We use this sentence to view only part of our mental model. So then we follow with the room has a supervisory desk and an incident desk. Note that here we say only room, not first or second room. So then we follow with viewing the supervisory desk. The desk has a telephone and 2 screens. Again, we need only say desk, not supervisory desk. Then we follow with the centre has air conditioning, which shows that we can still refer to an earlier topic centre if it can be unambiguously identified. And then we start to move out from our considerations by saying leaving the supervisory desk and then going back a further step like this, leaving the previous, an alternative way of saying the same thing.
This slide shows left the semantic net, corresponding to the previous set of sentences. Each viewpoint is effectively the root of a tree. When we search for a subnet, we start at this root. If the search fails, we try an earlier route, and so on.
This process of searching from a route, and then if the search fails, searching from an earlier route, as exemplified by 1 to 5 in the figure to the left, mirrors processes used in the scoping of variables in contemporary software languages. But further discussion of the mechanisms involved here really lies beyond the scope of this particular lecture.
Let's turn our attention now to sentence synthesis. We can only skim this subject. We can synthesize a sentence from our mental model by traversing a selected part of the model net. We may wish to stress certain topics in the sentence which emotionally we feel are important. We do this by applying weighted anchors to model nodes to guide the traversal. To the left, the upper example stresses Jack and the lower example stresses climbing.
With sentence synthesis, there are 1 or 2 basic rules. Going forwards via has, we get has in the synthesized sentence. Going backwards, we get of. But as noticed in part 1, of is often suppressed unless the previous node is a participle. Again, going forwards via is, we get is in the synthesized sentence. Going backwards, we get is by if the previous node is a participle, or of if not. Notably, if we ever backtrack through a node, we create a clause in the sentence.
Using these rules and starting at the node with the most stress, Jack, we get, for the upper net to the left, Jack is climbing of the hill. For the lower net, we get the climbing of the hill is by Jack. Note the clause of the hill created by backtracking via the climbing node.
We might want to keep the stress on climbing, but stress Jack more and the hill less. These stresses are shown to the left and result in the sentence, the climbing by Jack is of the hill. Again, the clause by Jack results from backtracking via the node climbing.
We can conclude this lecture now by having a brief look at synthesizing a sequence of sentences associated with describing something. Similar mechanisms to views and localization are invoked when we are asked to describe something based on information in our mental model.
When we give a good, well-organized description of something, we tend to move progressively from the general to the more specific. This corresponds to going up our mental model tree as in figures 1 to 8 shown to the left.
A less sophisticated way traverses the tree left to right, as in 1 to 7 left, and uses the view function successively on each tree branch. The result is shown on the following slide, which is actual output from the software application AI Dialog following the request Describe Jack.
So looking now at the sentences generated from the request Describe Jack, we have there is just one Jack, viewing Jack, Jack is a doctor, caring and skilled, Jack has a degree, viewing the degree is medical, leaving the degree, leaving Jack.
We pause here to consider a couple of technical topics. The semantic network is what is termed the directed graph data structure. It consists of nodes or vertices and directed edges between nodes, as shown to the left. Each node, as we have seen, carries a label which is generally a single English sentence word, but occasionally a quoted phrase or something even more complex. Each edge, in addition to its direction, carries data. This is always is or has.
We can contrast the graph with a tree data structure shown in the figure to the left. With a tree data structure, we can only ever have one edge going into a node, and the edges shown dashed in the figure are prohibited. This in turn has implications for any software we create to implement conversational AI. This software must be able to handle graphs rather than trees, which therefore impacts on its design. But this topic really lies outside the remit of this particular lecture.
A particular requirement of the graph handling software is its ability to perform a search to find subnet matches in our mental model net. This is termed an isomorphic subgraph search for matches within the main graph as shown below.
At this point, we've reached the end of the Part 2 lecture. Hopefully you found it interesting, informative and thought-provoking. There are just a couple of points to be made on the final slides which follow.
The software application AI Dialog gives a practical demonstration of most of the theory described in Part 1 and Part 2 of these lectures. AI Dialog can engage in a conversation with the user, accepting plain English input and responding in the same. AI Dialog comprehends user input and builds an internal mental model from this, of the type we have been discussing. It subsequently uses the model to respond to our queries, testing this comprehension.
The AI Dialog software application is protected by international copyright, but it is available as a free download for non-commercial private study purposes from a number of research data repository sites. It runs under Windows 10 or Windows 11 and requires about 1 megabyte of memory. The publication which is mentioned on the final slide describes its operation and characteristics and lists the sites from where the download may be obtained.
Again, of necessity, a lecture like this must, at times, skim over topics and be superficial in its treatment of them, to keep to a reasonable presentation timescale. To remedy this, these topics and additional related ones are dealt with in much greater detail and far more rigour in the book Artificial General Intelligence, A New Approach by Francis R. Belch, available from Amazon.com.